Now, let's look at analog circuits in terms of resistors. And we see here the basic three configurations of resistors, of connections of resistors. On the left-hand side, we see circuit with resistors in series. In series means that as we can see here in the picture, we have four resistors, one following the other, just like cars of a train. The output of the first one is basically connected to the input of the second one. The output of the second one is connected to the input of the third one, and so on and so on and so on. And this electronic circuit is basically driven by a battery, and it's closed loop circuit. In order for a current to flow, in order for this circuit to do something, it has to be closed loop. So we have four resistors in series connected, one side to the plus of the battery and the other side to the minus of the battery. On the right hand side, we see a circuit with resistors in parallel. We see two resistors, R1 and R2. They are connected in parallel, meaning that they are the both ends of both resistors, each pair is connected together, so they are in parallel. And as a parallel set, they are connected to the battery. The bottom picture is basically a mixed combination of resistors connection. Let's look at the green rectangular and the red elliptical. The red elliptical, as we mentioned just a minute ago, there are two resistors in series. Now, once we actually do something with these two resistors and come up with the equivalent resistance to the two, we will have an equivalent resistor which will be in parallel to the resistor on the right-hand side. Both of them will give us an equivalent resistance. So again, R1 and R2 are basically two series resistors, and we make up an equivalent to them. Once we have that, together with R3, which is in parallel, we'll get an equivalent resistance to that. And all of a sudden, we have kind of a new circuit. We have the three resistors on the top, and we have one equivalent resistors on the side. As an end result of the combinational and computations we did with the three resistors on the right. So this is kind of a top-level description of resistors in series, resistors in parallel, and resistors in mixed connection. I'm not going yet into some calculations. We will go it in short. But just to give us kind of a top-level picture. So here we start actually looking at the calculations of two resistors in parallel versus two resistors in series in an electronic circuit driven by a battery. Let's look at the left. The left half of the picture demonstrates to us two resistors in parallel. So we have a battery. It has a plus side and a minus side. This battery generates VB, voltage of the battery. And on the right, we have the R1 and R2, which are two parallel resistors. Now, the equivalent resistance to R1 and R2 in the case of parallel connection is demonstrated in the formula underneath. And this is only one of the formulas. We will go into more formulas. This is just one of the formulas that we can use. In case R1 equals R2, we can easily use the formula which is down there, which is 1 over the total resistance equal to 1 over R1 plus 1 over R2. Coming up with this computation, we will get the total R, the equivalent resistance to the two parallel resistors. Let's look at the current on the left-hand side. The battery generates voltage and also current. current is being generated because we have resistors in the circuit and because the circuit is a closed loop. So we have the major I current that coming out of the battery, and it's split into two halves in case R1 and R2 are equivalent. So this I is broken down to two halves, I1 and I2. I is coming into the junction. In this point of junction, split, and these two currents, I1 and I2, goes through R1 and R2 and combine together to be the same I as before, closing the loop, going back to the battery. So that's a top-level description of the currents and how to calculate equivalent resistance to a simple parallel resistor connection electronic circuitry. Let's look at the right-hand side. Same battery, plus side, minus side, and the battery provides VB. And the battery provides current because there is the resistance in the circuitry and because the circuit is a closed loop. And here we have two resistors in series. These two resistors in series, as we can see in the formula on the bottom, in case of serial connection, it's a summation of the resistance. So the equivalent resistance of R1 and R2 in the case of serial connection is basically the summation. It's R1 plus R2. And on top of across R1, across this resistor, because there is a current that flows, there will be a voltage drop, V1. We will look at this a little bit later when we will actually study Ohm's law. But that particular circuitry has only one current. This current is not splitted. It has only one loop. And this current goes through R1 and continue to go through R2 and continue to go to the minus plate of the battery to close the loop. And VB is basically the summation of V1 plus V2. That's how we actually break down the voltage drops across the two resistors. So this is the description, top-level description of series and parallel resistors in case of two resistors only. We will look at a little more difficult, not difficult, but more complex electronic circuitry using resistors. Now we're going a little bit, one layer down. Let's look at the top. Series connection. A battery, R1, R2, R3 are connected in series. One current, the current is in the blue color. We can see the direction of the current, and we understand that the equivalent resistance now in this particular case is R1 plus R2 plus R3. The parallel, the picture in the center, again battery, and we have three branches. There are no branches in serial. We have three branches in parallel circuitry. R1 is in parallel to R2 as in parallel to R3, and we can see that the current goes out of the battery. It's split into three sections, three segments, and it combines together on the bottom and comes back to the minus to close the loop. And the output current is equal, identical to the input current. We understand now how to calculate the equivalent resistance, but we will do some experiments, some calculations in a minute. Now the picture on the bottom is a mixed. Again battery. Two resistors R1 and R2 are in series, and then they go to R3 and R4, which are in parallel one to each other. There is a current going in. The current is split into two, comes back just as it was before. And here is a mixed example, kind of simplifying the branch. It's basically the same picture as before, but now we understand more about branching. The main current coming out of the battery going down gets to the junction point, split into two, comes back, combines, and comes back to the electronic circuit. So now we look at resistors. Up until now, we talked about two resistors in series or two resistors in parallel. Let's kind of make it a little bit more complicated. Here we have three resistors. So now we know that in series connection, the R total is basically the summation of all the resistance, R1 plus R2 plus R3, and if we will have 20, it will be all the way up to plus R20. In parallel connection of resistors, more than two resistors, if they are equal resistors, then we can go with the equation, the formula on the top, 1 over R total equal 1 over R1 plus 1 over R2 plus 1 over R3, etc., etc., etc. And we have another formula that we can use in case the resistors are not equal, R1 times R2 times R3 divided by, and we can see. So here we have two different formulas in parallel connection to solve the problem of getting a total resistance of an electronic circuitry. Something very interesting I would like to share with you about parallel connection of resistors where they are all equal. And in this particular slide, we can see 4 resistors connected in parallel, all of which are 10 kilo ohms in their resistance. 4 times we are equal, and if we look at the formula from before, 1 over 10 kilo plus 1 over 10 kilo plus 1 equal 1 over R total, we will come out with a quarter of these resistance. So the equivalent resistance of this particular circuit is quarter of each of them, 2.5 kilo ohm. And in resistance, just a simple example, R1 equal 5 kilo ohm, R2 equal 10 kilo ohms. 10 kilo ohms meaning 10,000 ohms. Ohm is the unit of resistance. Kilo is 1,000, of course. So we have 5 kilo ohms R1 plus 10 kilo ohms plus 7.5 kilo ohms. It's 22.5 kilo ohms. We add up all these resistors. 22.5 kilo ohms. Obviously, it's equivalent to 22,500 ohms. So now let's look at currents. Before we looked at resistance, now let's look at currents. And also, we are actually getting closer and closer to analyze more complex electronic circuitry using resistors and additional components, as we will see later. Here we have a battery, current coming out of the battery, split into 3 branches, I1, I2, I3, and coming back to the battery, which is basically the same as the current that went out. And if we actually apply Ohm's law now, before even we study that, just kind of a top level, we can see that the voltage across each resistor is equivalent to the voltage of the battery. They are all in parallel. There is a short on the top and there's a short on the bottom, and the resistors are connected in parallel one to each other and in parallel to the battery. Therefore, the voltage across each resistor is identical and it's the same as the voltage of the battery. Therefore, I1, applying Ohm's law before even we study that, I1 equal to V over R1, that will give us the current through resistor R1. And with the same idea, same formula, I2 equal V over R2 will give us the current through branch number 2, through resistor number 2 in this case, and I3 equal the V over R3. Remember, I put an emphasis on the fact that the only way I can do that, the only reason I can do that is because the voltage across its resistor is identical. So I3 equal V over R3, and the I input is equal to the I output, which is the summation of the input of the current in the 3 branches. On the left, I demonstrate what I said before. V of the battery is identical to V1, voltage across R1, V2, and V3. Now, in terms of the resistance, kind of a summary, kind of repetition to what we did before, but this is the place to do it. We can get a RE, which is the R equivalent, which is a one resistor equivalent to the three branches, the three resistors in parallel. 1 over RE equal 1 over R1 plus 1 over R2 plus 1 over R3. We can plug in numbers, get the resistance, get the current, get the voltage using Ohm's law, and we will do it in a couple of minutes. And these are three nice, simple examples. We have three resistors on the top, 6 ohm each, and I put an emphasis on the fact that they are identical. 6 ohm each, 3 times, meaning that the equivalent will be 1 over 6 plus 1 over 6 plus 1 over 6 equal 1 over the equivalent. If we run this calculation, we will get 1/3 of that 6, 2 ohms. Same idea with the 9 ohm, 9 ohm, and 9 ohm. The equivalent is 3, and this is only in the case that the three resistors are identical. 12, 12, 12 give us 4. Now let's look at from a current and voltage point of view. We looked at three resistors in series. On each of them, there is a voltage drop. On resistor number 1, there's a U1 voltage drop. On resistor number 2, there's a U2 voltage drop. And the resistor the number N on the chain of resistors, it will be UN. And the voltage across them, U, will be U1 plus U2 plus U3, etc., all the way up to the very last voltage drop on the very last resistor. In parallel, I1, I2, all the way down to IN, the input current is identical to the output current, which is the summation of all the currents. And here we have another type of summary of resistors in series and resistors in parallel using different formulas how to calculate it. I will go very, very quickly on this particular slide because I believe that we understand it now. We have 4 resistors in series. This is why the R equivalent, R total, is R1 plus R2 plus R3, etc., etc. If we have 2 resistors in parallel, is R1 times R2 divided by R1 plus R2. This is one way of doing it. If we want to find a specific resistor, we want to calculate specific resistor in our electronic circuitry, look at the right-hand side. R1 equal RT times R2 divided by R2 minus RT. So we play around, manipulate with the formula to take out the R1, and this is the resistor we're looking for. We want to calculate knowing the equivalent resistance. So the formula is a little bit changed. And equal resistors in parallel, the bottom half of the slide, again, we have in case the resistors are all identical, have the same value, the R total is R over the number of branches, parallel branches that we have, parallel resistors that we have, or the formula that we already went through, 1 over 1 divided by 1, to give us the R total. So this particular slide demonstrates to us that on each particular resistor, there's a voltage drop. And we can understand from this particular slide the direction, the polarity of the voltage drop. The plus side of the battery, which is the longer bar, is basically the plus side of V1. And if we look down on the minus side of the battery, in both cases, we can see that the left part of R3 is connected to the negative side of the battery. That means the voltage is minus on the left and plus on the right. And the plus on the right is connected to minus on the bottom of R2 and plus of the top of R2, which is connected to the right-hand side of R1. Negative and the left-hand side of R1 will be positive, and these are exactly like cars of a train. Plus is connected to minus on one side, minus is connected to plus on the other side, and this is how we chain all these voltages drop together to come out with the voltage of the battery itself.